So in this video we are going to learn how to obtain the record level of information to design air cooler or air cooled condenser. So whenever I say record level of information, what do I mean? We are going to rely on some hypothetical method which will give you some basic information such as the heat transfer area, so from which we can calculate something about the size of the air cooler, or we can calculate the space requirements. So whenever we talk about air cooler, it's going to occupy a huge space in the plant layout, so this is something we have to calculate. So this method will allow you to calculate the heat transfer area, from which we can get some information about the size of the air cooler and other parameters, size parameters involved in the air cooler. And then we can also calculate the space requirements. So we can also calculate the space requirements. So area, some information about the size of the tubes, and then the space requirements like length and the width of the air cooling unit, air cooler unit. And from there we can get some idea about the space requirements. And the air cooler also needs some fan to pull or push the air through the tubes which carries the process fluid. So we can also calculate the power requirements. So it's not a complete design or a full detailed design of air cooler, but it gives you some basic idea about what could be the heat transfer area and what could be the size of the air cooler or the entire unit, and then from which we can get some idea about how much space we need to install that particular unit, and then obviously the power requirements for the fan, which is normally used to push or pull the air towards the tube which carries usually the process fluid. Yeah. And then we will also learn some of the basic advantages and some of the limitations or the disadvantages of the air cooler. So this is something we will briefly cover. Not all the advantages and the disadvantages, but something that's related to the design of the air coolers. Before going into the topic, this is something you should know. So typically in a condenser, so what we are talking about at the moment is air cooled condenser or a air cooler. So what we use in a typical condenser, if we have to cool a stream, so we use or we select different type of streams to cool down a process stream, which typically comes at a higher temperature. So process stream, this is the stream that we want to decrease its temperature. Yeah. So we can use either air, as in the air cooler, and sometimes we can use the water from the cooling towers. So these are some common utilities. And then if there is any process stream which is colder, and if we have to raise the temperature of that particular colder stream, then we can use that colder process stream as an utility in order to cool down a process stream which is already at a higher temperature. So another process stream which comes at a higher temperature. So these are some common utilities. However, when we use an air cooled condenser, so instead of a cooling tower water or maybe another process stream which comes at a colder conditions, normally we will use air, and then the air, typically when we have some shortage of water, so when water is not the utility which is readily available to us, or if the process condition follows some of these specifications, say like if you have a process stream and we have to condense that stream, and if that particular process stream or a fluid, it has a property so that it can condense at temperatures not more than 20 degrees centigrade above the ambient temperature. Yeah, so this is one condition. Say if you have a particular fluid which has that can condense at a temperature, say if your ambient temperature is 25 degrees centigrade, and we have a particular fluid, let's call it a fluid A, and if this fluid can condense at say 45 degrees centigrade, then air cooler would be a good option, as this fluid can condense even at a mild temperature of 45 degree centigrade. So in that case, air cooler will become really handy and useful. So these are some of the conditions that you should know, like when to use an air cooled condenser. And the main disadvantage with respect to air cooler is that it requires a large ground area. So we will, when we are doing some calculations, you will understand what's the dimension will look like. And then obviously it involves fans. So air cooler contains fan. Typically it's a very huge fan, and it generates a lot of noise. So these two are some disadvantages of the air cooler. Yep. So in terms of setup, so how the air cooler typically looks like. So typically it may looks like something like the one which is shown in the figure here. Let's call it figure number 1, figure number 2. I have more figures to show you. Say figure number 3, figure number 4, and figure number 5. Yeah? So these are different schematics that should give some general idea about how the air cooler should looks like. So obviously you have something here. So these are the tubes where we typically send or pass the process stream, and you take the process stream at the other side if it's a one pass. If the fluid passes through the tube only one side, or alternatively it may contain something like here. So follow the pen. So you may also have some horizontal bundle of tubes. So you have some lot of tubes. So you have some horizontal bundle of tubes and arranged, and you have multiple rows. So typically 3 to 4 rows. So this is something you have to imagine. So horizontal bundle of tubes, and these tubes we may have up to maybe 3 to 4 rows. So you have something like that, and then you have one more row down. So this is 2 rows. So something similar to here. You see 2 rows of tubes, row number 1, row number 2, and this may be a horizontal bundle that goes towards the other direction. So that's the typical setup. So typically your process fluid flows into the tube. So you can see here, so some hot fluid flows in. So okay, if this is a 2-pass tube, so actually it flows through here, and then it passes through here. It may be an U tube, and then it comes back, and then it exits here. So probably there must be some separator in between. So this is like a 2-pass tube. So inside the tube typically you will have your process stream. So process stream that enters at a high temperature, and typically it leaves at a low temperature, and that's because we are cooling them using a fan which is fixed here. In this case we have 2 units of fan, and this is something we call it as a induced draft air fin cooler or induced draft air cooler, because what we are doing is the fan is on the top, so we are going to pull the air across the tubes, and these tubes are typically finned, so they are not bare tubes. So due to the low heat transfer coefficient of the air, so we are going to use some fins. So we will come back to this at a later stage. So why we use fins and how the tube typically will look like, this is something we can discuss later. But for the moment, so why we have a tube which contains a lot of fins, that's mainly to increase the heat transfer area. So soon we will discuss about the Cp value of air, which is very low when compared to water, and then also the heat transfer coefficient of air is very low. So that's why we are using the finned tubes. And another type of setup is shown here. So this is something we can call it as forced draft. So what we do here is so you have the same setup, you have 2 tubes, and again hot fluid passes into the one side. I believe this is an U tube, so it passes through this tube. So you have one pass, and then this is the second pass, and then it exits at the other side. So you get the hot fluid out here in this part. So it will go at a temperature T1, and then it will return at temperature T2, capital T suffix 2. And then here you have a fan in the bottom. So what you do is, instead of pulling the air through the finned tubes, it will push the air through the fin tubes. So it pushes the air through the fin tube. So these are the two different types of air coolers, and typically they occupy a huge space, and as I said, that's because of the low heat transfer coefficient. So which means the one way to transfer the heat for such system is to increase the area. So the amount of heat you exchange, that depends on this type of equation. So I will explain this equation very soon. So the Q is something related to the quantity of the heat transferred or exchanged. So if you have if the heat transfer coefficient is low, then which means your Q will be low, your Q will decrease. So one way to increase, provided your heat transfer coefficient is very low due to the very poor Cp of air. So Cp is something specific heat capacity of the air. If Cp is high, then it can transfer more heat per unit mass per degree centigrade. So that's the definition of the Cp. So since for air it's very low, one way to increase the Q value is to increase the area. So whenever you think about designing the air cooler, so two things that should come to, maybe three things that should come to your mind. One is your heat transfer area. This is going to be a massive number. And then this power requirement for the fans. So your fans are going to consume a lot of power because it has to pull a large volume of air through the finned tubes. So another one is the power requirements. So they both are not easy to calculate, but there are some easy methods. So this method was proposed by Robert Brown. So I will give the reference details probably later at the end of this video. I will also post something in the description below, the title of the manuscript and the journal name and the issue, page number, etc. So this is something I will add at the end of this video. A very useful method proposed by Brown. So it does not involve too many calculations, but it relies on a few hypothetical parameters and some crude assumptions that allows you to calculate this area, which is very important, and then it also allows you to calculate the power requirements. So let's go down. So this is the same setup of the air cooler. So this is induced draft, where you are pulling the air, fan pulls the air. So this is the unit where you have the tubes. You may have 2 to 3 rows, or maybe 4 to more than that, 4 rows, and these are some horizontal tubes. So sorry, I mean these are the horizontal bundle of the tubes. It may be a finned tube, and obviously you're going to use some fan to push the air or pull the air. So if you're pushing the air, it's called forced draft. If you're pulling the air through the finned tubes, it's called induced draft air cooler. So that's the typical setup of air cooler. This is something you should know. Since we are talking about the typical setup of the air cooler, I'm going to discuss about the number of rows involved, the tube rows. So you have some horizontal bundle of tubes. Typically they are placed in different rows. The number of rows can range typically from 2 to 6. Usually the most common number is 3 to 4. These are the number of tube rows. The number of passes, it can be 1 or it can be more than 1. So if it's a 1 pass on the tube side, so even if you have multiple rows, so in this case I have 3 rows of tubes. So if it's a 1 pass on the tube side, so your process stream enters on the one side and exits on the other side. So this is 1 pass in the tube side. So this type of setup. So typically your process stream, that comes at a higher temperature, T1, and exits at a temperature of T2. So this is one pass on the tube side, and then typically you pass the air across the tubes. So let's say your air temperature is T1 and then it exits on the other side at T2, and typically these tubes are finned tubes, so they are not going to be bare tubes, so we are going to use the finned tube in order to increase the heat transfer rate by increasing the heat transfer area. Yeah. So these are that's the typical setup for one pass on the tube side. And alternatively, if you have a multiple pass, so your process stream can take more than one pass. So in that case, imagine you have an U-tube, something like that. So your process stream can enter one side, it takes one pass, and then it comes through passing through the U-bend, and then it returns to the other side. So this will be second pass. So this is two pass in the tube side. So again, your process stream enters at T1 and then it exits at T2. So that's the typical setup. If you have a two pass in the tube side, and again your air will passes across the tubes, so your air temperature will start from T1 and then it leaves at T2, small t2. Yeah. So for convenience, we are going to, in this video and also in the next video where I will solve a model problem showing how to design the air coolers. So we're going to stick to this notation. So T1 it means a T1 comma T2. So they are the process stream typically. So they enter the tube side, and then T1 and T2. So this is the temperature of the air that enters on one side, and that T2 is the temperature of the air that leaves on the other side of the air cooler. So in this case, T2 will be less than T1. So this is for the process stream, and T2 will be greater than T1. So this is for the air. Yeah. So capital T means hot fluid, small t means cold fluid. In this case, cold fluid is just an air. So far so good. So now so far we learned like when we use the air cooler, and the typical setup of an air cooler, what's an induced draft air cooler, what's a forced draft air cooler, and then we also talked about the typical tube arrangements in the air cooler and why we use the finned tubes. And then I also talked something about the tube arrangement and then the number of rows that you can expect. Then something that you should know more about the number of tubes is, I'll write it here. So the number of rows typically range. So typically the common number of tube rows is number of rows of the tubes is 4. So typically you have horizontal bundle of tubes, and typically you have 4 rows, 1 2 3 and 4. But there are some other cases where this number can change. So the rows, you may use only 2 rows of tubes. If the process stream that enters and something that exits here, so T1 T2, so if the temperature difference between T1 and T2 is only less than or equal to 10 degrees centigrade or 10 degree Fahrenheit. Yeah. So if this is the case, then you have to use 3 rows. So you use 3 rows of tubes if the difference between the process stream that enters the tube side and exits the other side, so the T1 and T2 is less than 10 degree centigrade. Yep. And then, so this is condition number 1, and then the second condition is again the same. Your process stream enters at T1 and then it leaves at T2. So if the temperature range of the process, not the temperature, the temperature range of the delta T, which is T2 minus T1, sorry, T1 minus T2. So if this value falls between 10 degrees centigrade to 20 degrees centigrade, then again we use 3 rows. So practically, if your T1 minus T2 is in the range of less than 10 degrees centigrade to 20 degrees centigrade, then typically we use 3 rows of tubes. So typically we use 3 rows of tubes. And then the third condition is, so again you have a process stream, something that enters. So it don't have to be one pass. I'm just drawing it for my convenience. It can be a multiple pass, more than one pass. So something that enters at T1, the process stream leaves at T2. As I said, T2 is less than T1 because we are cooling this process stream using the air as a medium, as a fluid. So if the difference between T2 and T1, so that is delta T equal to T2 minus T1. So if this range between 100 degrees centigrade to 200 degrees centigrade or Fahrenheit, and if the assumed overall heat transfer coefficient, heat transfer rate, and assumed overall heat transfer rate U if is less than 80, so then assume 5 rows. And then there is one more condition. So if the temperature difference between T1 minus T2, if this ranges from, say, again 200 degrees centigrade to 300 degrees centigrade, and the overall heat transfer rate is less than 40, then we assume we need to use 6 rows of tubes. So 1, 2, 3, 4, 5, and then 6. So this is condition number 4. And then finally we have one more condition, 5. So if the temperature range of the process fluid, so say here from here to here, so T1 to T2 is greater than 300 degrees centigrade, and the overall heat transfer rate is less than 30, then we assume 8 rows. 1, 2, 3, 4, 5, 6, 7, and 8. Some of these numbers sound weird, but this is what I learned from the article written by Robert Brown. So this is, so at the moment we are following the procedure proposed by Robert Brown. Yeah? Enough introduction about the air cooler. So now we can go to design. So let's start to write the procedures required to design the air cooler. Yeah? So let's write air cooler design procedures. So as I said, this is the method proposed by Brown. So we are just following his ideas. So whatever we learned so far is some general idea about the air cooled condensers. So we are going to see now the general procedure to get the so-called initial estimates. Yes, it's called initial estimates to design an air cooled heat exchanger or an air cooler. Yeah. So what do you mean by initial estimates? So we are going to use some method that can provide some basic information about the heat transfer area. This is something I said earlier, and then based on which we will get some rough estimate on the space requirements and the power requirement. So as I said before, this method relies on some hypothetical parameters. I'm going to show those values. So these values is something that you need to design the air cooler. Yeah? And so this method was proposed by Robert Brown, and he also provided a lot of numbers that we absolutely need in order to get some idea about the number of tubes, the length of the tubes, from which we can get some idea about the space requirements, and then area of the tubes, and then obviously the power requirement. So this is our ultimate goal. So we need to know the number, length, and then the size of the unit, and then the power requirements, and some idea about the heat transfer area. Like any heat exchanger, the main parameter that dictates the air cooled heat exchanger is the heat transfer area. So this is the one that dictates everything involved in the design calculations. So this can be obtained obviously using the basic expression. This is something you should have learned from the heat transfer module, given by Q, which is equal to UA delta T LMTD. So this is something you should know. Log mean temperature difference. A is the heat transfer area, U is the overall heat transfer coefficient, Q is something related to the heat transferred or the quantity of the heat exchanged. So this is your heat transferred. This is the basic expression. This is something that you should know by heart. So this is overall heat transfer coefficient. So delta T LMTD is something we can call it as effective temperature difference. So I will tell you how to get this one. So this is the effective temperature. So the procedure to design an air cooler goes like this. So what we are trying to calculate is the heat transfer area, which is A. So it's something that you can get from this basic expression, UA delta T LMTD. So to get this value, you should know your T1, you should know T2, you should know T1, comma T2. So this is the temperature of the process stream that enters the tube side. This is the temperature of the process stream that exits the tube side. So these two values, this is something we already know. T1 is the temperature of the air, and T2 is the expected air temperature that leaves the air cooler. And U is the overall heat transfer coefficient. This is something that we can calculate based on the type of fluids involved. And Q, this is something that we can obtain from process simulation softwares, like example ChemCAD, Aspen HYSYS, or this is something that we can even calculate mathematically. Maybe I will put a separate video on how to get this Q for a particular system. Yeah. So this Q value is something we have. Assume that we obtain this value using some process simulation software for a particular system that involves some particular type of fluid that may contain one or more components. I will tell how to get this value. So there is a table provided by Robert Brown. I will show you what's that table, how it looks like, and from there we can calculate area. So to calculate area, at the moment we assume we have Q. Let's assume we can obtain the Q from the table provided by the Robert Brown, and we have T1, we have T2, we have T1, and then small t1, and then we have to calculate small t2. So T2 is the exit temperature of the air stream. So how to get that one? So you can get that one from using the expression provided by Robert Brown. So T1 minus T2 equal to 0.005 heat transfer coefficient multiplied by T2 plus T1 divided by 2. So this is the average of the process stream temperature minus the temperature of the air. And note that to apply this equation, everything should be in degree Fahrenheit. So using this expression, you can calculate the temperature difference on the air side, or the fluid which we are using to put the process stream temperature down from T1 to T2. I mean capital T1 to capital T2. So T2 small t refers to the air stream. So air is our utility at the moment because we are talking about the air-cooled condenser. So how to get this value of U? So we'll show the table provided by Robert Brown. So let's go to the table. So this is the table 1. So these are the approximate. So these are not actual heat transfer coefficients. So these are the approximate overall heat transfer coefficients. So what Robert Brown did, so typically in a air-cooled heat exchanger, so you get the finned tubes. So typically you get the finned tubes. But for the convenience, Robert Brown, he assumed at the moment we are using just bare tubes. So he called them, these are some hypothetical tubes with the heat transfer coefficient that should be equivalent to the heat transfer coefficient that you can expect in a finned tubes. So these are some hypothetical numbers. So these are some approximate numbers for the overall heat transfer coefficient. So how to use this one? For example, if you are dealing with say for example, say maybe it's just some heavy oil, so then your corresponding heat transfer coefficient is 6 to 10. And then say if you're dealing with say like ammonia at this particular pressure 10 psig, then the corresponding heat transfer coefficient is typically ranging from 10 to 15. So these are some numbers provided by him. And then if it's for example kerosene, so we are going to solve some problem using that involves kerosene in the process stream side. So the corresponding heat transfer coefficient range from 55 to 60. So that's the table that you have to use in order to get the approximate overall heat transfer coefficient for air-cooled heat exchangers. So actually the original paper from the Brown, he just mentioned these are approximate numbers. And until this point he didn't mention that these numbers were arrived for finned tubes or for the bare tubes. Yes. Oops. So let's use this table in order to get the first value, which is the heat transfer coefficient, which is U. So once you get the U value, so I'm going to write the procedure here. So get the U value. So this is the approximate heat transfer coefficient. This is the approximate heat transfer coefficient. This is something that you can get from table 1 of the Brown paper. So once you have this U value, so we know what's the T2, we know what's the T1. So T2, this is something we should know. So what's the temperature that we are targeting? So if we know the process stream enters at T1, and we should know what should be the exit temperature T2. Yeah? So this is the temperature that we are targeting. And then we also know the dry bulb temperature of the air, which is T1. And from this we can calculate T2 using this expression. So the first step is to get U value. Second step is to get T2 or T2 minus T1. And in the Brown paper, he also mentioned that, so the U values in the table 1, which I showed you just now, so they are for different fluids. So it involves several fluids. And based on that, he calculated that, so 1 by H0 plus 1 by Hi. So H0, this is something related to the heat transfer coefficient, or the resistance to the heat transfer on the air side. So if you have a tube, you may have some film on the air side. So this is the resistance to the transfer of the heat on the air side, on the outside the tube. So So this value, and this is something, so if you go to Colson and Richardson, you can get the HI value. So this something gives about resistance to the heat transfer, or if you take the inverse H, that's something gives about the heat transfer coefficient, on the process fluid side. Yeah, so inside the tubes. So why we take here inverse is that's because U gives the heat transfer coefficient, so this is not additive, but whereas the resistance to the heat transfer, which is given by 1 by U, that's an additive function. Yeah? So 1 by H0 plus 1 by Hi plus something, if you expect something on the wall side, so then you can add the resistance cost to the heat transfer in the wall. So this is something that you can write. So based on this expression, Brown calculated the value for the heat transfer coefficient for the air film. So if you have a tube, you will have some tiny air film, and the heat transfer coefficient through that air film is around 75 BTU per hour feet square degree Fahrenheit. So this value is extremely low, and that's why Brown suggested that we need a finned air tube. Yeah? So this is some common sense. Yeah? So if your heat transfer coefficient is low, one way to improve them is to increase the quantity of the heat exchanged is to increase the heat transfer area. So that should obviously increase the quantity of the heat exchanged through that area. So if the area is more, you exchange more heat. So that's the whole concept. So let's go back to the actual design problem. So we calculated U, we calculated T2 at the moment. So once you have U, and then once you have T2 minus T1, from there we can calculate area using that expression Q is equal to UA delta T LMTD. But Brown suggested that, so if you directly use this value T2 minus T1 that we calculated using that expression, then that should give an area which is approximately 25% plus or minus to the optimum value. So say if your optimum value is equal to 100 feet square, then the area that you calculate based on the delta T LMTD obtained from this T2 minus T1 value, that will be equal to plus or minus this actual value. So it can be 75 feet square or can be 125 feet square. So to make this accurate, in order to calculate the A value accurately, so Brown gave some correction factor to estimate. So to estimate the temperature rise on the air side. So temperature rise on the air side, T2 minus T1. So he gave some correction factor. So we can apply that correction factor. So that comes from the chart provided by Brown himself. So let's check this. So this is the correction factor. So follow the pen here. So this is the chart provided by Brown, figure 1. So you can see the title here, correction factors for the estimated temperature rise. So we know this value of T2 minus T1, which is plotted on the X, capital T2 minus capital T1. So this is the temperature difference in the process stream side, plotted on the X axis, and then the temperature rise on the air side, which is plotted on the Y axis. So based on that value, we can get the correction factor. Say if the temperature difference on the process fluid side, say is like 100 degrees centigrade, change the color, it's around 100 degrees centigrade, and then say that T2 minus and the corresponding correction factor for the T2 minus T1, which is on the air side, should be equal to, go to the Y axis, so it's approximately around say 1.02. This is something that you can check by using the graph. Okay, so once you have the correction factor, so you go back to the problem. So how to get the correction factor? Obviously you have to use the figure 1 in the brown paper. So you have T2 minus T1 and then the correction factor for the rise in the temperature in the air stream. So this capital T2 minus T1 on the x-axis is the drop in the temperature on the process stream side. So from there you get some graph, so you can calculate the corresponding correction factor. So once you get the correction factor, you can change, so you can multiply the actual T2 minus T1. Okay, let's go back into the top. Let's call this equation 1. So T2 minus T1 from equation 1 multiplied by the correction factor obtained from figure 1 in the brown paper. So now you have almost everything that you need to calculate the area. So you have T2 after applying the correction factor, T1, you have U value, you have delta T value, you have Q, which is the heat transfer rate. From there obviously you can get the area. So the area should be given by Q by U delta T LMTD. That's so far so good. So Q is the quantity of the heat transferred. This is given in BTU per hour, something like a rate. And then U is the overall heat transfer coefficient, BTU per hour, feet square, degree Fahrenheit. And T is, at the moment we are using it in degree Fahrenheit. Delta T LMTD is obviously dimensionless, so no dimensions. So delta T is LMTD. This is nothing but your effective temperature difference. So obviously this depends on the temperature difference on the process fluid side, which is T1 minus T2, and also the temperature difference on the air side, which is T2 minus this effective temperature difference, or the delta T LMTD. This is something you know how to get this value. So LMTD, this is equal to, so the T2 minus T1 minus T1 minus small t2 divided by natural log of capital T suffix 2 minus small t suffix 1 divided by same this parameter here, which is capital T suffix 1 minus small t suffix 2. So capital T suffix 2, process stream that exits the tube side, T1 temperature of the process stream that enters the tube, T1 inlet temperature of the air, T2 exit temperature of the air. So once we get delta T LMTD, so we also need to get, so if you remember this delta T LMTD, so this is the log mean temperature difference as it appears in the conventional heat transfer books. So log mean temperature difference for a counterflow arrangement with the same fluid inlet and outlet temperatures. So note that this value delta T LMTD is applicable only if you have a counterflow arrangement. So sometime in some textbooks they also add this notation delta T LMTD comma CF. So this delta T LMTD is applicable only if you satisfy this condition. So if you have a fluid process stream, something that should be heated from T1 to T2, and on the other hand you also have some cold fluid starting from T1 with temperature rises to T2. So for a perfect counterflow arrangement, then this equation holds valid. But if you look at your actual air cooler, so you have some tube side and then you have some cross flow, so your air flows like this, so there is no counter current arrangement. So in that case you have to calculate we have to calculate delta T LMTD comma CF, so which is equivalent to delta T LMTD. So we can calculate delta T. So we can calculate delta T LMTD from the information that we have, capital T1, capital T2, small t1, small t2, but we have to find the equivalent value of delta T LMTD in a typical counterflow arrangement. So for that, what we need to do is to convert delta T LMTD, or to calculate the delta T, which is its equivalent delta T LMTD in a typical counterflow arrangement. We need to apply a correction factor, some number which is called correction factor. It's called that factor just F. So the delta T LMTD CF, that should be equal to correction factor multiplied by the actual delta T LMTD. So what this factor, so this factor, correction factor, this correction factor depends on a range of parameters. So this is a function of, this is a function of something called P, I will explain what, and then something called R, and then your flow arrangement. So this also dictates your delta T LMTD. So as I said, this delta T LMTD is valid only if you have a counterflow arrangement. So if you have a different type of flow, then obviously this value is going to change. So that's why this correction factor depends on your flow arrangement. So what P corresponds to? So P is equal to small t2 minus small t1 divided by capital T1 minus capital T2. So what's this one? So capital T1 is obviously the temperature of the process stream that enters the tube side, and T2 is the temperature of the process stream that exits the tube side, and then T2 minus T1 is nothing but the actual temperature rise in the cold fluid. So what does this mean? So this is just the numerator side is just the heat actually transferred to the cold fluid. So this is the heat transferred to the cold fluid, something in temperatures like a degree centigrade or a degree Fahrenheit. So divided by T1 minus something is not correct. So T1 minus this should be T1, small t1. So capital T1 minus T1. So small t1. What does this mean? So this is the heat that which would be transferred. So the denominator T1 minus, let me change this one. So this is T1. So capital T1, this is the temperature of the hot stream or the process stream that enters the tube side, and T1, this is the temperature of the air which we are using to cool the process stream. So this is the inlet temperature of the air. So what should be this difference? So capital T1 minus small t1. So this would be the heat, let's write it, the heat which would be transferred, the heat which would be transferred if the same fluid were to be raised to the hot fluid inlet temperature. So the T2 minus T1, so this is the amount of heat that we transfer to the cold fluid side, and then T1 minus capital T1 minus small t1. So this corresponds to the hot fluid, this corresponds to the inlet temperature of the cold fluid. So what this temperature difference means? So example, if your T1 is 100 degree centigrade, say your small t1, which is your cold fluid side, which is equal to say 30 degrees centigrade, and the difference between them just gives 100 degrees centigrade minus 30 degrees centigrade, so 70 degree centigrade. So what it means is, so you cannot transfer more than 70 degrees centigrade from the hot fluid side to the cold fluid side. This is something we can call as the delta T maximum. So it is impossible to transfer more than this temperature. So if you manage to transfer 70 degrees centigrade, then you achieve 100% efficiency in transferring the heat from the hot fluid to the cold fluid. But this is not the case. And then what we actually transferred is small t2 minus t1. So let's call that one amount of heat transfer to the cold fluid side. So let's give some, that's equal to delta T suffix C. So C refers to the cold fluid side, and then delta T max refers to the maximum amount of the heat that you can theoretically transfer from the hot stream to the cold stream. So actually the ratio of delta C divided by delta T max. So this is something that talks about your efficiency. So we can call them as temperature efficiency. So what do I mean by that? So if your delta Tc is equal to delta T max, so if you manage to heat the temperature which is equal to delta T max, then I mean like if you manage to heat your cold fluid which enters at T1 to T1, which is the inlet temperature of your hot fluid, then your delta Tc will be equal to delta T max. So in that case, delta Tc will be equal to delta T max, then the ratio, this will be equal to 1, which means theoretically you achieve 100% efficiency, but however, this is impossible to do in practical life. So that's the P is something related to your temperature efficiency. So this is irrespective of your type of flow in the process stream side. Yeah. So it can be a single pass, it can be two pass, or it can be more than two pass. Then how to define R? So R is given by capital T1 minus capital T2 divided by small t2 minus small t1. So what's this? This is something related to the temperature rise on the temperature drop on the hot fluid side. So temperature drop on the hot fluid side with respect to the temperature rise cold fluid side. So in recording the video, I think I just mentioned R is something is equal to heat capacity rate ratio to be precise, which is correct. However, I mentioned that it is the ratio of the heat capacity rate, the hot fluid, divided by the heat capacity rate of the cold fluid. So this is not correct. So this should be exactly the other way around. Also, let's correct this one. So what it actually should be, this is equal to heat capacity rate of the cold fluid, I'll tell you why, divided by heat capacity ratio of the hot fluid. So this is something that can be defined if you know how to write R, which is equal to T1 minus T2 and then T2 minus T1. So in the denominator we have the temperature difference in the cold fluid side, in the numerator we have the temperature difference we can expect in the fluid, in the hot fluid to be precise. So what does this mean? So this is something delta T with respect to hot fluid divided by delta T with respect to your cold fluid. We know this relation Q is equal to mcp delta T. So delta T of hot fluid, this is something equal to Q by mcp with respect to your hot fluid, and then delta T of cold fluid equal to Q by mcp with respect to your cold fluid. So you can plug these values to get some idea about or to define R, which is given by these ratios of temperature difference in the hot stream and in the cold stream. Yeah? So something R is related to something like a Q by mcp of the hot stream or hot fluid divided by Q mcp of the cold fluid. So actually this MCP goes to the numerator, this MCP comes to the denominator. So in the textbook, this is something, if we want, we can even write it like a Q MCP of the. So this is also equal to something equal to, so R, which is equal to capital T1 minus capital T2 divided by small t2 minus small t1. So this is approximately equal to Cc divided by Ch. So what's this Cc? This is something related to the heat capacity, yeah? Capacity of the fluid to transfer heat divided by of the hot fluid side, heat capacity of the cold fluid. So these values apply no matter which stream is on the which side, whether your process stream can be on the shell side or on the tube side. Nevertheless, this rule applies. R is equal to T1 minus T2 divided by T2 minus T1. So that's why we are using the terminologies hot fluid and then cold fluid, irrespective of where they flow. Where it can pass through the shell side, the hot fluid, or the hot fluid can pass us through the tube side. Nevertheless, this equation holds true. Yeah? So now we defined something called temperature efficiency, and then now we defined something related to the heat capacity rate ratio. Yeah? So this is the, it's actually heat capacity rate. So R is heat capacity rate ratio. So the heat capacity rate of the hot fluid divided by the heat capacity rate of the cold fluid. So for the case of a for the case of air cooler, so this is our tubes. It can be more than one row, and then your air flows through, something like a cross flow, across the tubes. So definitely there is no counter current arrangement. So once you get the delta T LMTD, we have to find the equivalent delta T LMTD for with the same fluid for the same temperature difference T1 comma T2 comma capital T2 comma capital T1 small t1 comma small t2 for the same temperature values for the same type of fluids. What could be the equivalent delta T LMTD in a typical counterflow arrangement? So if you are using the same fluid and if you are expecting the same temperature difference in a typical counter flow arrangement, what could be the corresponding delta T LMTD? So this we can get by multiplying the actual delta T LMTD with the correction factor F. So this F depends on P. If you know P value, if you know and R value, then we can get the correction factor from the correction factor chart. So these charts were originally prepared by the authors called Bowman for most of the multiple pass, shell and tube and cross flow heat exchanger. Yeah? So typically F value will be less than 1 for cross flow. So this will be the case for air cooler and multiple pass heat exchanger. So multiple pass, it can be either on the shell side or it can be on the tube side. So it doesn't matter. Eh? So in a way, so delta T LMTD divided by F. So this value just gives some idea about the degree of departure, from the true mean temperature difference that can be expected in a counterflow arrangement. That can be expected in a counterflow arrangement. So that's the purpose of applying a correction factor. So I have some graph here which I can share with you. So this is something that we can use for to design air cooler. So let's go up. So it's something you have here. So what do you have here? Okay, here in this graph we have a different notation, so I'm going to write what we have here. So what we have here on the x-axis is just p value, which is nothing but the temperature efficiency, which I define now, and on the y-axis you have correction factor. So this is something that we need to calculate, especially for air coolers, because a typical setup of the air cooler is something shown here, the tube layout. You have different type of tube layout. So you have multiple rows, 1, 2, 3 rows, and these are the horizontal bundle of tubes in each row. So you have 3 rows and the horizontal bundle of tubes on each row. And then here your inlet stream, which is your air, comes through here and then it passes through out. In this type of setup, your air passes through somewhere here and it goes to the other side of the shell side. So typically for air cooler, we can expect this type of setup. So you have tube bundles here, and then you can air that goes inside and then air that leaves on the top. So that's a typical setup, and this, let's assume this is for one pass on the tube side and one pass on the cell side. So where air passes through one time and then it leaves on the top. So for such a setup, so this is the corresponding graph of P versus correction factor for different values of the heat capacity rate ratio. So this is something, your heat capacity rate ratio R. So ignore these ones. So if your R value is 0.2 and if your P value is 0.9, say for example, so just draw some line like that, go to the top and then go to the corresponding ordinate, which is on the y-axis. So this could be 0.86, that could be your corresponding correction factor. So that's how we have to use this graph, and this graph, it also provides some additional information. So that's something we can discuss as we are talking about temperature efficiency and also the correction factor. So if you look at this graph, so you have P value here, you have R value here. So P value and then your correction factor starting somewhere from 0.5 to 1, and then your P value somewhere ranging from 0 to 1 here. So what does that mean? If the temperature change in one fluid is negligible, that is either P or your R value, the temperature change in any one of the fluid is negligible. That is if your P is equal to 0 or if your R is equal to 0, then your F value is unity. So in that case, no matter whatever the configuration of your heat exchanger, it can be 1 pass, 2 pass or multiple pass on the tube side or on the shell side, your correction factor is going to be 1. So this typically happens when you have if your fluid went through a phase change. Yeah? And your R value, so you have some range 0.2 to 8.0. So actually this R value can range from 0 to infinity. Your R value can range from 0 to infinity. Actually that 0 corresponds, if R is equal to 0, it corresponds to complete condensation, or your all the vapor completely fully condensed. And the infinity, if R value equal to 0, that refers to vapor condensation. If R is equal to infinity, that refers to complete evaporation of your fluid stream. And I'll also note that if your F value is equal to 1, it does not mean that your heat exchanger is completely efficient or highly efficient. So it means that whatever the flow which is happening inside your heat exchanger, so that is equivalent to the expected flow pattern in a typical counter flow setup. So that's the the meaning of this graph. So let's go back to the actual design problem. So at the moment we are designing air cooled heat exchanger, and if for the air cooler, if you have only one pass and then on the process stream side and one pass on the air side, and this is the chart that you have to use in order to get the correction factor. So we will come back to this chart later. So let's go on. Let's continue with our intention, which is to develop the design protocol to design the air cooled condenser. So why we talked so much about delta T LMTD is we can get delta T LMTD, and then we have to apply the correction factor in order to get the equivalent delta T LMTD that can be expected in a counterflow arrangement for the same type of fluid with the same temperature difference on both process stream side and on the air side. So delta T LMTD in a typical counterflow arrangement. So now we can calculate Q is equal to UA delta T LMTD CF. So this will be equal to this part of the expression. So once you have the area, so you have Q U delta T LMTD with the correction factor involved. So now we can calculate the actual area of the air cooler. So Q divided by U delta T LMTD expected in a typical counterflow arrangement. So once you have this area, then again we have to go to the one of the table provided by Bell. So let's say for the moment our area, something that we calculated, is equal to say 2284 feet squared. So this is just an example. So let's say we calculated this value. So from this value we can get some information about the number of tubes, the length of the tubes, using the table provided by Brown. So this is the one of the table, just to follow the pen. So this is the table provided by Brown. So this is, he assumed that at the moment we do not have any fins. He assumed we are using a bare tube, which is far from reality when we think about air cooled condenser. So nevertheless, we can use this method for the moment to get some approximate idea about the number of tubes that we need, how long should be the tubes, and so on. So these are some hypothetical parameters, but very useful to get some idea about the dimensions involved in a typical air cooler. So the value which we saw, which is I said our value is 2284. So if that's the area, either you can select this. At the moment we have 2284 in this table, and then we can also select another value which is closer. This value should be higher than the actual calculated value. So say if your actual value is 2283, then you have to select this one, 2284. This value should be greater than the value that you are checking in the table, must be greater than your calculated values. Okay. So what does this mean 2284 means? So you may need number of tube rows should be 4, and then you need 2 fans per unit, and then the tube length is approximately 40 feet, and then the approximate unit width is around 14 feet, and all these values that you see here, Brown assumed the tube size is 1 inch outer diameter in a triangular pitch. So for this value of 2284, so we need number of tube rows. So number of tube rows is 4, and then number of fans that we need is 2, and then tube length is 40 feet, and then the width is 14 feet. So from here we get some idea about the number of tubes, fan requirement, and also the space requirement. So these are some of the benefit of or the usefulness of the Brown's method. And still Brown assume we are using bare tube. So if you know the area of the bare tube, then we can calculate the area of the finned tube. So typically if you add a fin, so if your area of the bare tube is 100 feet square, with the finned tube will be 20% of this 100 feet square, which will be 20 plus the actual area of the bare tube. So your finned tube surface will be approximately 120 feet square. So that's the idea. So you get some idea about area. From area you already calculated all the important parameters. So the only parameter now which is missing is the power requirement for the two fans. So just remember this number 2284. So how to get the power requirement? So this is something that we can get from the chart which is provided somewhere. So this is there is a chart, useful chart, that allows you to calculate the fan power requirement for air cooler. So for that you need overall heat transfer coefficient, where U value, and then from there you can get the fan power in horsepower per feet square of the bare tube surface. So if you have some U value, say for example our U value is 55 BTU per hour feet square degree Fahrenheit. So this is somewhere around here, and then that should be equal to, let's put a dotted line here. So this should be equal to approximately 1.56 horsepower per 100 feet square of a bare tube surface. So still this is not finned tubes. So we can use the same chart for finned tubes. All we need is to multiply. We can add approximately some area for the fin, maybe 20% of this number. So for the moment we assume everything is bare tube. So let's assume this should be equal to 1.56 horsepower per 100 feet square. So let's go down. So if our area is 2284 feet square, we know that we need 1.56 horsepower per 100 feet square. So we can calculate the total horsepower requirement, power requirement for 2284. So feet square, horsepower. So 1.56 for 100 feet square, you need 1.56 horsepower. So therefore for 2284, we need 2284 multiplied by 1.56 divided by 100. This should be equal to 35.63 horsepower. So this is the power requirement for the two fans per unit with the dimension which we already discussed. So that's how we design the air cooler. So in the next video I will try to solve an example problem where we will have some value for Q. We have to get the U value. From there we have to get delta T. From there we calculate T2, and from there we will calculate delta T LMTD. Then we will apply some correction factor. So we will use that correction factor chart, and then we calculate the area. From the area we will use the chart or the table values provided in the Brown's paper. From using area we will get the number of rows, tubes, length and width, and then we will also get some estimate the fans required, number of fans required, and then the power requirement for the fans. So thanks for listening.